this is a question on the, this is the second video for Math 107 homework number 3 on polynomials. So in this case we're practicing the rational root theorem, and the rational root theorem says that all rational roots will be fractions made out of the factors of the leading term, leading coefficient, and the constant. So the idea here, although it seems like mathematically wrong, would be to, let's look at the leading term. It's 1. All the factors of 1 are going to be 1 itself and minus 1. You just list them, because 1 times 1 would give you 1, 1 times minus 1. Now that looks like it's wrong, but it's one of the factors. Right? Now we'll look at the constant, which is 2, and write down all the factors. There's going to be a 2, and a 1, and a minus 2, and a minus 1. Okay, that's all the factors for that. Then you make fractions out of them. You put the constants in the numerator, and the leading coefficient here goes in the denominator. Right, the factors of it. So I'll let the 1 be in the denominator for a while, and I'll put all these in the numerator. So I'd have 2 over 1, 1 over 1, minus 2 over 1, minus 1 over 1. There's usually a lot of duplication in here. Now let the negative 1 be in the denominator and put all these others in the numerator. 2 over negative 1, 1 over negative 1, minus 2 over minus 1, and minus 1 over minus 1. Now go ahead and, get rid of all the duplicates and reduce your fractions a little bit. So 2 over 1, that's 2. 1 over 1 is 1. Minus 2, that's a 1. So, oops, how did that get positive? Okay, that should be a negative 1. I'm going to get negative. Now, this is a minus 2. You already have it in the list. This is a minus 1. You already have it. This is a minus 2. Well, that says a positive 2. You've already got it. And minus 1 over minus 1 gives you 1. So this is your whole list right here. These are all the possible rational roots. Now here's the deal. What kind of roots can you have? You can have rational roots. You can have irrational roots. 0 isn't included in here. And you could also have complex conjugates. So this only covers the rational roots. Now at this point you're going to use this list to find the actual roots of this equation. And there's several ways to do that. Probably the easiest way is to put these into that equation and see if they equal 0. Equals, you don't know yet, 2 cubed minus 2 times 2 squared minus 2 plus 2. Well, that's obviously 0, so this is a root. It's one of the roots. Go back and try the 1, try the minus 2, and try the minus 1. And that's the easiest thing to do. You could also divide the polynomial by x minus 2, and there's other ways to test them. Okay, this is a bisector method. Now I like this method. This is a method that's used in numerical methods. This is how things are solved on the computer these days. Many times we need to work through things, and it's good to do things analytically, but some things belong to a computer, and this is one of them. And this is what's called the bisector method. The trick is to separate what you're averaging. And I'm going to draw a few, get the line. Okay. So I want to get this idea down first. So these are my axes. So okay, we can see those. And this is the y-axis, and here's the x-axis. Now polynomials, actually they're what's called smooth, but they're continuous functions, meaning that there's no jumps or gaps in the graph of them. So if I start and I know there's some value that's positive here for a polynomial, and over here I know some value's negative, I know that even though it might swoop around, it has to somewhere cross 0. Because it has no jumps, it can't jump over the x-axis and get there. It has to cross it. And I'm looking for this point right here. This is the goal that I'm looking for. Alright? So say I know that this is, I use the n's and p's. You can use whatever you want. Okay, let's say this is 10 and this is 1. So I know when x is 10, it's negative. When x is 1, it's positive. Somewhere between 1 and 10, it crosses the x-axis, and there's the number I'm looking for. So to find this number by the bisector method, I take the 1 and the 10. Don't take the values of the function here and here. That's not the method. The method is to take the x values and average them. So my new value will be 1 plus 10 over 2. Obviously going to give me 5.5. So let's say 5.5 is right here. Change color. So here's 5.5. Now I have a question in my mind, so I found a new value of x. My question is, what is the value of the polynomial at 5.5? So if I put the 5.5 back in the equation, I didn't draw this particular equation, I just drew another one for illustration purposes, I find that it's positive. So I know it's positive at 5.5 and negative at 10. I know the root is somewhere between these two. How do I find it? Well, I get a little closer by taking another average. I would go 10 plus 5.5 and divide by 2, which is going to give me 7.75. Okay. So here's my 7.75. Now my question is the function positive or negative? Because I've drawn it, you can see it, but if you don't know, which you won't when you do the problem, you take the 7.75, put it back in this equation, and find out if it's positive or negative. In this case, it happens to be negative. So I know the roots between here and here. I average 5.5 and 7.5. You see I'm getting closer and closer. I'm sort of cinching down on the root. The trick is average the x values, not the y values. And all I want you to do is 3 iterations. An iteration means you took the average and you found out kind of whether the polynomial was positive or negative, so you knew which side to average. For example, if I found out that 5.5 was negative, I would have averaged in this region, because I need one positive, one negative on either side of the sort of trap where I'm trapping that zero, that root of the polynomial. Now we move to rational functions, and in a rational function there's a polynomial in the numerator and a polynomial in the denominator. Typically they're called p in the numerator. That's a polynomial in the numerator. Here's a polynomial in the denominator. And this chart got kind of scrunched, but what you're supposed to do in the first row here is give the general requirements. What is the requirement for vertical asymptote? At a vertical asymptote, the denominator is 0. That means q is 0. You have to find the values of x that make q 0, and that's where your vertical asymptotes are, because at that point the function is not defined because you have 0 in the denominator, but near that 0 the function either goes towards positive infinity or towards negative infinity. And that's why it's called a vertical asymptote, you remember. Now state the general requirement for an x-axis intercept. When it intercepts the x-axis, the y, which is the same as the function, is 0. So to make this 0, the numerator has to be 0. So you need p to be 0 for an x-axis intercept. Now that's the general requirement. Now you go down and look at these and try to figure out what values of x would cause this. Let's look at this case right here. What would cause the numerator, this is the numerator, p of x to be 0? Well, if x is 0, that'll do it. So this graph, the function, if you graphed it, would cross the x-axis. I'm sorry. Where x is 0, the value of the function would be 0. Now in the denominator, I need to find a value of x, or values of x, there's going to be 2 of them, that would make this 0. So you set it equal to 0, and okay, you might have to factor it. Okay, so what 2 numbers multiplied together give you minus 10, added together give you 15. Alright, we'll say x plus 20 and x minus 5. So I just factored that equation. So what values of x make this 0? Well, x of minus 20, x of negative 20, and x of 5. So those are the 2 vertical asymptotes. X equal minus 20, x equals 5. Okay, when you get down to this one, this f of x, remember that you can factor an x out, so one of the roots is going to be x equals 0. And here, for the x-axis crossing, you have to set the numerator to 0. Find the value of x that would set this to 0 for this column over here. Look at this equation. Is there any value of x that will set 4 to 0? No. So there is no x-intercept.